Number 3, section 5.2. Find the characteristic polynomial and the eigenvalues of the matrix. Okay. Let me write down the matrix. Really, the whole point is to find all the eigenvalues directly from the matrix. Okay? And there is a nice simple technique for doing that. So just remember, lambda is an eigenvalue if it satisfies this equation for some non-zero x. And that's equivalent to saying the same thing for this equation. All right, so here's the idea. When you subtract lambda I from A, you're really subtracting just lambda from all the main diagonal elements. All the other elements are the same. All right, now you might remember, and by the way, this has to be true for non-trivial x's, so you don't count the zero column. But you might remember this equation, or any equation that looks like this, only has non-trivial solutions if A is not invertible. That's part of the inverse matrix theorem, okay? So we kind of want to force this thing to not be invertible, okay? If it's not invertible, then this will have non-trivial solutions. So that's kind of the idea. So remember, it's enough to look at the determinant of this matrix to decide whether or not it's invertible. If the determinant is 0, it is not invertible, and we will have non-trivial solutions. If it's invertible, we're only going to have the trivial solution. So the idea is take the matrix of this thing, or I should say the determinant of it, and try to force it to be 0. Because if you can force this thing to be 0, that will force this system to have non-trivial solutions. Because if it's invertible, you're only going to get the 0 vector for the solution. So that's kind of the idea behind the characteristic polynomial. And the characteristic polynomial is just this determinant expressed without the absolute value bars. So this is a 2x2. It's kind of easy. Just this minus this, that's the definition of the determinant of a 2x2. You just have to take that guy and simplify it a little bit. So that minus negative 28, and that'd be 20 minus 5 lambda minus 4 lambda plus lambda squared plus 28. So whatever lambdas will satisfy that equation will be eigenvalues. Should kind of make sense. And it looks like minus 9 lambda if you combine these guys, and 48 is the constant. All right. And actually, they just asked us for the characteristic polynomial. So I did a little more than they asked us for. They really just wanted this thing right here. So I could solve that thing for lambda if I wanted to, but we just wanted the characteristic polynomial.